Everyone. I'm so glad every students from Tishk University will be available here and from different university, of course. And thank you so much for Mr. Ilham for this opportunity to talk to you about the 3D printing. And the title is to be presented here is about 3D printing technology and fourth industrial revolution in construction industry. So hopefully I'm talking about this title and I'll be finished on time. Just trying to take on time. All right. So can you go to the next page, please? All right. So okay. So about the 3D printing, like additive manufacturing or rapid prototyping, it can be divided into two major parts. It's called additive and subtractive. Additive, it means we're adding stuff on each other, and subtractive, we are removing stuff. So like engraving. So CNC machine is the best one to describe as a subtractive. So maybe there is different machines, but CNC machine most useful, and I think it's available now in Kurdistan and Iraq, mostly using for advertisement. As an additive manufacturing, there's many types of additive manufacturing, but so far not has been used in construction industry, or we can say they have a lack for civil engineering purposes. The most common one that have been used, it's powders and liquid and sheet. So the liquid one, it can be most popular one, like extrusion printing. And the powders as an inkjet printing, it can be most useful one. And I can show you later on how it can be used for our purposes. And in the Industrial Revolution, it started from the first Industrial Revolution in mid-80s. Like a mechanical production that we have been using in Britain, UK. Then later on in Britain again, the second revolution started in mid-90s. Later on, and third revolution starts from early 20s. This one is early 20s. It started from after, we can say, World War II, and become more computer and automation in our manufacturing, and using robots, especially for manufacturing the cars, as well as for aeroplane. But after that, they have a lack from the mid 20s until now, especially for civil engineering. They cannot produce it much, and they cannot change it or evolve a lot. But in manufacturing, it was grown very quickly, and they have a lot of production, especially for mechanical engineer, for the engine, for the cars, for the aeroplane. But for construction industry, it really stops. So it doesn't move much to better quality, or we can say better production. So the fourth industrial revolution actually starts in 2016. We can say early 21st. So especially the cyber systems coming, like having artificial intelligence and Internet of Things. And 3D printing, one of them actually, it is part of the cyber system, or we can say part of the fourth industrial revolution. I'm going to show you two images here. Maybe it's very popular for you. I think it's Bardargi Slemani. This one, have you seen any change in these two photos? Maybe this is a question for you guys. One of them in a black and white, the other one in only color. So there is not much change actually in construction, like in construction as an industry. So we have two photos, but almost similar for construction. But if you go to have a look at the manufacturing industry, especially for mechanical engineers, we can see a lot of changes. If we pick one of them, like a Mercedes-Benz in 1885, and Mercedes-Benz now in 2022, you can see a lot of changes, right? So in the appearance of the color, in the structure of the color, and even the car, you can use it as a home, as your house, because it has everything inside it, right? So you have air conditioning, you have even TV inside your car. So there is like a big changes. We can say how manufacturing industry grows quickly. And again, manufacturing industry revolution. If you see in 1900, like an American car company, how many peoples in the manufacturing process they are contributing? Like you can see how many peoples inside the company. But now you can see all the car companies completely shifted to robotic arms. So you don't need much labor. So because labor costs a lot. Therefore, if you see, you can, all the manufacturing process now in Europe and USA, using a robotic arm because it costs less and it's much faster and so accurate than the human. They can do their jobs very quickly and very precise as well. Another one, in a construction, we have something called formwork. And the formwork, have you seen any changes in the formwork? You can see in the pictures on the left in 1912, and the other pictures on the right in 2022. Is there any changes? We are using similar formworks. So maybe the formworks changed from the different types of material, like a timber, or you can say wood to metal. But still, we are using similar process. So all the process same. If you are looking at formwork in a general system, we have 3 types formwork system. Traditional one, the wooden and metal one. The other one is called flexible. The flexible inside it is digitally fabricated formwork and fabric formwork. These 2 formwork, it's our discussion in this presentation, especially digitally fabricated formwork. And the other one, recyclable formwork system, as we have sand one, the ice formwork. So the formwork cost in construction, if we are looking at this diagram, it shows us clearly that about 45% cost is in the formwork. How? The formwork's labor cost is about 34%, and the material itself about 20%. But this is not quite exact number, so it maybe varies from project to another project, that it can be changed from 40 to 60%. So according to last literatures I've been reading about, it changes about 35% to each project to 60%. So that's a major changes that we want to do in construction. How we can remove formwork, instead of that using digital life, or we can say mechanical machine like a 3D printer. So first of all, when you do any 3D printing, first of all, if you see the 3D printing, one of the types called binder jetting 3D print or inkjet 3D printing. We have been using this printer in University of Technology, Sydney. I've been completely modified the material. We have been using instead of gypsum, cementitious material like a mortar, completely mortar. It can be used for this kind of technology. and we can use for all construction purposes. Actually, people maybe say, oh, this is a mortar, maybe it not work properly, but mortar, it is similar like ultra high performance concrete. So we can use it for all construction purposes. So you can use different type of materials. We can use a particle size, very small or fine, and use it for all purposes. And we achieve a very good result for the construction. This process is a layer by layer as well, but using the droplet of the water on the powder. And the process actually takes longer time than the extrusion process. Also, the powder is flowing from the back of the printer instead of the paper coming out, the powder coming. And the rotors help us to the powder flowing out from the printer, from the back of the printer. So those pictures you can see like Opera House, UTS, you can make any geometry that you want. So it is complicated geometry can be affordable in all life. Those geometry that you are not in your thinking, you can make it by 3D printing. So large scale 3D printing actually have been invented by Codini, he used a D shape. But this kind of material is a magnesium, like a magnesium silicate, some kind of this material that have been used. It's not exact cementitious material that in construction we have been using now. And in the past, still we are using Portland cement, but we try to use a different kind of material. I think this is back to 2012 that he manufactured this machine and make it this kind of shape. Another kind of large-scale inkjet printing in Germany, it's a voxeljet. And this kind of voxeljet also, they try to do kind of the mini house with the help of University of California. So as you see on the right side, this is making the mini house by this kind of the printer. And during like 72 hours, you can make everything that you want. So in regard to the extrusion printing, we have been using different kind of robotic arms, like we have been using ABB robots, and we have been using also Denso robots. I'm not sure if the video working or not, but it maybe no works. However, both of the robots make similar things, but we are pumping the material out to the head of the robot, and we make it the material quick to harden and capable to bear all the layers. This is one of the type of the we have been using two different universities, one of them UNSW, the other one in UTS. For the large scale extrusion printing, we have now printed houses. So one of them, the first one on the left, you can see in Icon 3D printing in Mexico. The other one, Apiscore 3D printing in UAE, in United Arab Emirates. And the last one, Perry made this house in Germany. So now in Europe, they are building bridges and they are trying to standardize as well for houses. So it means this is work properly, but we need different types of material. For example, we are using accelerator. As Mr. Hauras talks about the different kind of material, now material develops very quickly, and it helps a lot in civil engineering field. And another types of printing that we need in construction, it is steel printing. Steel printing now also faster than concrete printing because it's much easier because it doesn't have issue of hardening, because a concrete is fresh. When it's fresh, it's like a toothpaste. So you cannot deal with it properly. But as a steel, we don't have that issue. As you fuse it, it will be hard in itself. So you don't have that problem much. And they are now made bridges in Amsterdam, in Holland. So different types of the machines you can use it, like a selective laser melting and selective laser sintering. I've been using that selective laser sintering. It's very cool machine. You can use it also for concrete, but in a different way. The image on the left, you can see it's made by MX 3D printed pedestrian bridge in Amsterdam. And this other one, SLS printed parts, they made it for engine and parts for the aeroplane. So now most of the aeroplane, they make the parts from out of the 3D printing because it's very accurate and very fast than the human made. So, and most important experimental tests that we should consider overall I'm talking about for concrete especially, we need to use a direct shear test that we are using for soil mechanics. This is most possible using to check the shear test in this material, especially in fresh state. And squeeze flow test, I've been using that test in 2019. Rheology tests, rheology, I mean, talked about like a thexotropy of the materials, such as shear thinning and shear thickening. So because of the concrete, if we have a water cement ratio over 0.4, it changes the behavior, especially for self-compacting concrete, changes the behavior from shear thickening to shear thinning. So we should, this test is contain a lot, like rheology, it is not just one test, it's too many tests you should consider. Flow table test, especially this is for flowability and slump. So usually we have a 0 slump in 3D printing. Setting time as well, we should consider that because we are using or dealing with the accelerator actually. And for 3D printing, we should consider all the time that we have a window, or in another word, we have a one time frame that we can print it in. If it is too slow, we have a problem. Why? We have a problem because it makes a cold joint with the next layer. If it is too fast, we have maybe issue with the collapsing. As you saw in the Brianci's presentation earlier, the all layer will be collapsed on each other. So that window is very important. I have been published that paper in 2020, and I've discussed that about especially the velocity of the robotic arm. So mechanical strength result on the printed materials, on printed concrete. I had that paper was published with a few colleagues in different universities. I've been collected all the kind of papers on the 3D printing, especially on compressed strength. We have achieved that some of the studies, they achieve about 100 megapascal. Some others, like Brianci, he actually Khalil, he achieved about 87 megapascal. And myself actually achieved about 50 megapascal in extrusion printing. So in steel as well, like a stainless steel colleague of mine, Laggy, she achieved about 613 megapascal in tensile test for steel, because in steel we really need the tensile test, no compressive one. So and most popular manufacturing system is called WAAM. It means wire arc additive manufacturing. So this is most popular one that you are using in stainless steel production. Regarding the Inkjet 3D printing, there is too many papers that talked about the binder jet, how it works, especially on the binder cement. There's papers published in Germany by Gillan and Uyghur. So they show how changes varies, but I can say on myself, in 2020, I published a paper. So in RILEM conference. So we achieved it about 40 or 37 megapascal in Inkjet 3D printing. So it is very prosperous for our future, so that we can use those kind of materials to print our houses. So because it's quite enough in that strength, you can build any houses that you want. And we actually use glass fiber as well in our printed material. So the glass fiber, it helps to reduce the shrinkage inside the material as well. So this is very hopeful for our future to have more study on the inkjet 3D printing. I just want to pick up all in one conclusion. For the 3D printing, one of the colleagues asked the question, why the 3D printing will be different from the other kind of the casting? Yeah, it will be different. So as you see in this figure, Hyperion Robotic and Pico Group, they built the kind of foundation or footing for transmission electrical poles, and they are optimized. So it means you can optimize your concrete. It no need to use all type of concrete or bunch of concrete in one footing. So you can optimize it and you can reduce the amount of the concrete in your construction. And also you can use a geopolymer material, not just cementitious material. It will be more sustainable for our environment. In spite of that, I want to talk about a little bit on steel one. The steel manufacturing, like wire arc additive manufacturing, it can be easier or more practicable than the concrete one. As you can see, by Arab in 2014, they built this kind of poles for construction purposes. So you can make any geometry that you want and optimize your material. So how we can optimize it? Of course, you can do the simulation and using finite element analysis. By this way, it will be best way to produce the best kind of materials in construction and reduce the amount of the material in construction purposes. Thank you so much for your time. Thank you so much being here all the way. Maybe coming from different universities, different places. Again, thank you so much for Tisch University. And thank you so much for Zilamo to be a partner of this event. I'm free to, if you have any question, please feel free to contact me or ask me a question. Any questions? Yeah.
As a structural engineer, I would like to know something about the distribution of the steel reinforcement actually in the shear wall, for example, for the 3D cuts, as you mentioned in Arab Emirates, I think.
Right.
How can we make these parts safe against wind loading or seismic loading? How can we distribute reinforcement?
Can you show that?
In the shear wall?
Right. So there's many studies have been done on shear wall and retaining wall, especially by Professor Kloff in Germany. Now he's working not only just on 3D printing concrete, he's working on shotcrete 3D printing. So he achieved this very promising result, and he achieved the result that 10% times higher than the normal shotcrete that we are using by Nozzleman. So this is very optimistic for our future that we are using robotic arms instead of the Nozzleman. So I can give you the articles about that. So if you just type shotcrete 3D printing on the Google Scholar, I'm sure you get a lot of results on the shotcrete. So if you go to last page, please, conclusion. Actually, this pole that made it by the Hyperion Robotic, it contains also the steel. Some of the steels you can be added by ball and nut, so like a screwed bolt inside, and you can replace your rebar inside any kind of element for the structural purposes. So, but in terms of the durability, we need more time to see if we have a crackers, especially like a crackers in a shrinkage or a creepers in our structural element. We need about 3-4 years until see what's going on with this kind of foundation. Yeah. Thanks. Any other question?